Hello, pirates and other random internet dwellers here who have stumbled upon our page talking about nuclear reactions. So, nuclear reactions are a kind of a weird subset of reactions, and they're not fairly typical that you would see in a first-year chemistry class, because in typical first-year chemistry classes, we're looking at usually chemical reactions. What is a chemical reaction? Well, a chemical reaction looks and is governed by the law of conservation of matter, that atoms cannot be created or destroyed, they can only be rearranged. So if you were to start with a carbon and two oxygens, you can combine them to create a carbon dioxide. Please be aware that over here on the left-hand side, we've got one carbon, and over here on the right-hand side, we've got one carbon. And over here on the left-hand side, we've got two oxygens, and over here on the right-hand side, we've got two oxygens. So we really haven't changed anything as far as the number of atoms are concerned. We've simply smushed them together. That's a chemical reaction. Carbon on the left, carbon on the right, oxygen on the left, oxygen on the right. The same atoms are there, they're just rearranged. Same thing here when you make water out of hydrogen and oxygen. Over here, you've got 4 atoms of hydrogen, 1, 2, 3, and 4. And over here on the right-hand side, you've got 4 atoms of hydrogen, 1, 2, 3, and 4. So again, the number of atoms and the type of atoms hasn't changed. Over here on the left-hand side, you've got 2 oxygens, and over here on the right-hand side, you've got 2 oxygens. So the atoms haven't changed. All we've done is rearrange them. Here, they're separated, and here they are together to make something new. These are chemical reactions. The same number of atoms that you start with on the left is going to be the same as you end with over there on the right-hand side. And that is what 99% of the reactions that we look at here in a first-year chemistry class are concerned with. However, in a nuclear reaction, what you are doing is you are actually messing with the nucleus itself. The atoms change. Now, people have been trying to do this since the dawn of time. The ancient alchemists and philosophers thought that way back in the day, if they did things right, they could take something like lead and turn it into gold. That was what all of the ancient alchemists were trying to do. They were all unsuccessful, obviously, because you cannot technically do that. But that doesn't mean that a lot of people didn't try. From way back in the day, people like Mary Prophetessa, and if you're a fan of Harry Potter, he mentions Nicholas Flamel in the first book. Nicholas Flamel, I guess, was actually a real guy who was an alchemist. And then even our buddy Isaac Newton, who did all sorts of great things for physics and so forth, was an alchemist who kept trying to figure out ways to take base elements and turn them into things that were more valuable, like gold. And technically now it's possible, but we don't have nearly the amount of control over it because it involves changing the nuclear process, changing the nuclear makeup of an atom, and adding or subtracting protons and neutrons until you get to that right number. And while, like I said, it's technically possible, it is tremendously difficult to do because you are changing the core of the atom itself, and we just don't have that much control over it. Having said that, you can turn one element into another element. And sometimes these things occur naturally, and sometimes we can force them to occur. But what's important for you to recognize here in this first year class is our nuclear way of representing these different elements. So, for example, here's lithium with 3, and then it's 6.941 as far as its average isotopic mass is concerned. So this picture here is showing us a typical lithium nucleus, and this typical lithium nucleus here has 1, 2, and 3 protons that are there, and then it's got 1, 2, 3, 4 neutrons that are there. And those 3 protons and 4 neutrons go together to make 7 overall for its atomic mass. And if you remember back from first semester, we covered all of this already. When you project and represent it this way, the number down below here represents the atomic number, which is the number of protons that are there. Here they are, 1, 2, and 3. There are those 3 protons. And the number up top here represents the number of protons and the neutrons put together, which is 7, which is the 3 protons and the 4 neutrons together. 1, 2, 3 protons, and then 1, 2, 3, 4 neutrons, which is 7 overall. That is there. So that is a representation of an atom of lithium-7. That is there. Carbon-12 is represented this way. If you look on the periodic table, you'll notice that it's got 6 up here as far as its atomic mass is concerned. So that means I've got 6 protons. So there they are, 1, 2, 3, 4, 5, and 6 protons, which is why the number down here is represented with a 6. And then this isotope is carbon-12, which means that it also has 6 neutrons. Here they are, 1, 2, 3, 4, 5, 6. There they are. And the 6 protons and the 6 neutrons get added together to make the 12 that is there. Now, all of this is old news. We talked about all of this last semester. I'm just reminding you of this notation so that you can remember how this works, because it's going to be very important for our discussion. So, in spite of the fact that all of these alchemists tried like crazy to turn these different elements into other elements, there are only some elements that do this naturally, and others we can force to do it, although we don't have a great deal of control about it. And the reason has to do with what's called the band of stability. Now, again, I'm not going to get heavily into this. I'm just going to point out that this graph here shows you the number of protons versus the number of neutrons in a typical isotope of an element. And these blue dots here represent all of the stable isotopes of the elements that exist. Please recognize that as you get more and more protons, or as you go further this way on the graph, the blue line of stability here curves upwards, which means you need more and more neutrons to counteract the repulsive effects of those positive protons as you jam more and more of them into the nucleus. The point is that as you get more and more and more protons shoved into a nucleus, the atoms become less and less stable. And eventually, you'll reach certain points where the number of protons and the number of neutrons that you have aren't right, and the isotope isn't stable. And when it's not stable, it can undergo a number of different processes, one of which is called nuclear decay. And nuclear decay is a naturally occurring process where the nucleus tries to correct itself because it has either too many protons or too many neutrons or too much energy or any one of a number of other more complicated things that are there. And this picture here shows the different types of decay that are possible for an unstable nucleus to try to correct itself. Now, this looks very complicated, and it is. We're going to try to keep it simple. Just please be aware that we're going to focus on only 3 of the types of decay. We are going to focus, first of all, on what is called alpha, and then we are going to look at beta negative, and then we're going to look at one that's not even listed on here called gamma. It's the easiest of them all. So when we look at the alpha, which is the yellow, that tends to be, if we looked at this in a very simplistic way, and if we looked at this line here as our divider line. If you are looking at alpha, those are the yellow ones. And if you look at the beta negatives there, those are the blue ones. And the alphas are the yellow ones, and they tend to be when you have too many protons. In a very generalistic sense, if you've got too many protons that are in the nucleus, that's where your alpha comes into play. That's what the symbol alpha is there. This guy here is Greek for alpha. And if you've got too many neutrons, that's the blue one here, that's the beta negative. That's the beta that's here. And then the nucleus is going to do something to fix itself by doing beta negative decay that's there. And then if it's got too much energy, it's going to undergo what's called gamma. Each of these is described in these next pictures here. Alpha is when you have too many protons and you've got a really big nucleus. Beta is when you have too many neutrons. And what actually happens there is a neutron turns into a proton and an electron, giving off an antineutrino as well. Don't worry, I'll explain more of these in detail as we go on. And gamma is when there is too much energy that is there. So here are the symbols for them. That's alpha. That's beta. And that's gamma. So if you see these symbols here, that one looks like a goldfish. So that one is alpha. Beta looks like a bee, but it has a tail. And gamma kind of looks like a 2, a cursive 2, if you turned your head over there on the side. Those are the 3 basic, simple types of radiation that we are going to be examining in the next pages here. Alpha, beta, and gamma. And they each have their own advanced symbols that you will see and you will need to know how to use for nuclear chemistry. Alpha, you'll notice, is 4,2He. A beta is a 0, -1, and E. And gamma is the easiest one of all. It's 0, 0, gamma. I'm going to look at each of these in turn and look at how each of these different particles or energy will affect the parent nucleus and how it turns into the daughter nucleus that's there. You'll notice that there's other notations and symbols here as well for things like protons and even positrons. And there are other types of things. There's a positron emission and electron capture and so forth. Like I said, we're not going to get into those. We're just going to keep it simple with alpha, beta, and gamma that's here. Just note that there are other types of things available, and if you're interested in those, take further chemistry classes. But for an introductory chemistry class, we're going to keep it simple to the basic 3. Alpha, beta, and gamma. Those are the ones that we are going to focus on here. All right, so enough for the overview. Now let's get into what is happening here. Let's start by looking at alpha decay. Alpha decay is basically when you have too many protons. So alpha decay is when you have too many protons. And what you have is you have a large unstable nucleus here, and then that kicks off what's called an alpha particle, which gets rid of some protons for it. Now, the thing that you have to be aware of is that every time something undergoes an alpha decay or gives off an alpha particle, what you have to know, and the only thing that you have to remember, is that an alpha particle is 4,2 helium. It's 2 protons and 2 neutrons that have been shoved together. And so every time it says alpha, you need to do 4,2He. That's what it kicks off. All right? So if we take a look, for instance, here at this parent nucleus, we have an atom of uranium-238, and it's going to undergo an alpha decay. So it undergoes its decay event, and please recognize that it gives off 2 protons and 2 neutrons, which is 4,2He. And then what's left is a daughter nucleus of 234 and 90, and all of a sudden that uranium has turned into thorium over here. So how did we know? How do we know that this thorium is going to come from this atom of uranium-238 over here? Well, that's some really easy, simple mathematics, and let me show you how this is going to go. So let's take a look at this guy here. 23793 neptunium, and it says it undergoes an alpha decay. So what did I say? Every time you undergo alpha, you have to do the following. You have to kick off a 4, and you have to kick off a 2, and you have to put an He. That's an alpha particle. Right? Sometimes in other texts you might see it as 4,2 alpha. You might just see it because it's tough to show both of the numbers. Sometimes you might just see it as 4He, because the 2 is kind of redundant, remember, because the 2 tells us the atomic number, and if we check out the periodic table for helium, we see that the atomic number for helium is indeed 2 that's there. So every time it's helium, we know it's 2, so we don't have to put the 2, but it is going to make our lives a lot easier if we do. All right, so what's going to happen here for our alpha decay? Well, it says that I've got 237 up top, that's the mass, and I've got 93 down below, that's the atomic number. And again, why is it 93? Because Neptunium, if we come down here and find Neptunium here is number 93. Please note that every time you look up one of these things on the periodic table, you can always trust the atomic number, the small number, but you can't necessarily trust the atomic mass because the numbers on the periodic table for the bottom numbers are the average of all of the isotopes, which is why you sometimes get fractions and decimals and so forth. But you can always trust the top number. So if it's manganese, it's always going to be 25 protons. If it's cobalt, it's always going to be 27 protons. If it's helium, it's always going to be 2. You can always trust the top number. So anyway, I've got 237 and I've got 93, and I just gave off 4 from up top and 2 from down below. So what does that leave me with? Well, that's some simple mathematics. If I started with 237 and I gave up 4, well, then what am I left with? Well, I'm left with 233. Because 233 minus 4 gives us 233. If I started with 93 down here, and I gave off 2, then I'm left with 91 down here. So, once again, all you're going to do is make sure that everything on the left-hand side up top is the same as everything on the right-hand side up top. So the 237 that's here is going to be the same as the 4 and the 233 that's up here. All you have to do is make sure everything on the left is the same as everything on the right. Down here, I've got 93. Now I gave off 2. That means I'm left with 91, or to put it again another way, everything that was here for my 93 is the same as everything that's over here. It's just been split up. So the 2 and the 91 go together to give me the 93. I just have to make sure that my numbers are the same on both sides. So if we go back up here to this example up here, then the 238 was where I started. I gave off 4 because I gave off an alpha particle, and that gives me the 234 because the 4 and the 234 go together to give me the 238. Same thing that happens down below here. I've got 92 for my uranium, but I gave off 2, and so that leaves me with 90. But how am I supposed to know that this is thorium? Because I started with uranium, I gave off helium, and how am I supposed to know that that's thorium? I get the numbers, but how am I supposed to know the symbols? Well, we already know how to do that because we know how to check the periodic table, and we know how to check the numbers. So, helium was 2. Helium is always 2. Uranium down here is number 92. So, uranium is always 92. But what element is number 90? Because we turned 92 into 90. Oh, 90 is no longer uranium. 90 is now thorium. So, that's why it turned into thorium. So, the 92 that was for the uranium here, the reason that's uranium is it's 92. The reason this guy is helium is because it's 2. And the reason that this guy is thorium is because he's 90. So remember that the bottom number tells us the identity, the smaller of the two numbers, I should say, tells us the identity of the atom, and we can find those on the periodic table. So over here, we started with number 93, which is Neptunium. So here's number 93 on the periodic table, Neptunium, there he is. And we gave off helium, which was number 2. There we go. We gave off 2 of those protons. Again, that's here. We gave off 2 of those protons. So what element are we left with? Well, we're left with element number 91. We just don't know what that element is. We just got to look it up. So we go back to our periodic table, and we find element 91 on the periodic table, and apparently it's protactinium Pa. So I would then put in this guy here as being Pa. So what's important is not the symbols as much anymore. We're not keeping track and balancing the symbols themselves. What we are doing is keeping track of the numbers that are there and making sure the symbols match our new numbers. So once again, please just be aware that ultimately everything on the top on the left-hand side of the equation is the same as everything the top on the right-hand side of the equation. It's just going to be split up. Everything on the bottom of the left-hand side of the equation is going to be the same as everything in the bottom on the right-hand side of the equation. It's just going to be split up. And then your symbols are going to change because you're no longer the parent nucleus that you were over here. You are now the daughter nucleus that you have turned into over here. Let's try another one. I've got 24195 americurium, and it says that it undergoes an alpha particle emission. No problem. Every time it's alpha, it's 4,2 helium every single time. No exceptions. So if it says it undergoes alpha, then you're going to start with 1, and then you're going to give off a 4,2 helium. So then what does that leave us with? Well, I had 241, and I lost 4, so that's going to leave me with 237 up top. And then I started with 95, and I lost 2, and that's going to get me down to 93, which is some other element. I just have to look up what that element is. So I'm going to come over here, and I'm going to find element number 93 on the periodic table. There he is. Element number 93 is neptunium. So this is going to be in P, like so. All right, what if I have some radon here? Some radon 222, and it undergoes an alpha decay, because again, we're going to undergo alpha particle emission. So if that's the case, I'm going to do 4, 2 with He, and then all I have to do is make sure that my top numbers match. So I need some number here that's going to go with 4 to give me 222, so obviously I'm going to need 218 up top, because the 218 and the 4 go together to give me the 222. Just make sure everything on the top matches mathematically. And then I got 86 that's here, and I lost 2, so that means I'm going to be at 84 down here, because once again, 84 and 2 go together to give me the 86. Those go together to give me that number. Everything on the right is the same as everything on the left, and now I just have to look up what element 84 is, because off the top of my head, I don't know. There it is. 84 is polonium. So that's element PO that's there. Hey, please just be aware that my correct answer here is polonium 218. Now, when you look it up on the periodic table, it says polonium should be 209. Am I wrong? Well, no. Once again, the numbers on the periodic table are the average of all of the possible isotopes of a particular element. On these equations, we are just looking at one of those isotopes. Okay? So that's alpha decay. Every time you undergo alpha decay, you do a 4,2 helium. Too many protons. What about beta decay? Well, in beta minus decay, which is your typical beta decay, what you typically have is too many neutrons. And if you have too many neutrons, then what's going to happen is that neutron that's here is going to turn into a proton and an electron, because essentially a neutron is a proton and an electron that have been combined. And what happens in a beta decay is the neutron kicks off the electron and says, see ya, that's you, and now turns into the proton like it shows there. So what happens is that a neutron turns into a proton. And if we take a look at this diagram here, then you'll notice that I've got 2 neutrons and 1 proton over here. And then after undergoing a beta minus decay, I now have 2 protons and only 1 neutron. So one of these neutrons that's here, this guy here, that neutron has turned into a proton by giving off an electron. Now this one gets a little confusing because it involves negative numbers. The thing that you have to remember is every time that you see beta, you're going to do the following. This is the important bit. 0, -1, and E. That is a beta particle. Sometimes you might see it as 0, -1 with a beta particle, like so, because remember a beta is a bee with a tail. But the important bits here is that it's 0 and -1. And the negative numbers tend to mess students up sometimes. Let's make sure that that doesn't happen to you. So let's take a look at this. Now again, we're keeping it simplistic, so not only does this give off beta particles, it also gives off things called antineutrinos. We're not going to worry about those, so we're not going to worry about where that comes from. Check out what happens in our math. Remember that everything on the top left has to be the same as everything on the top right, and everything in the bottom left has to be the same as everything in the bottom right. So please be aware here that what we've got is we've got 3 on the top left, and then we have 3 on the top right and 0. So 3 and 0 is the same as 3. I'm good. And then what happens, though, is I've got 1 on the bottom left, and this is where things get messed up. And I've got 2. Well, how did 1 turn into 2? Well, remember, you're going to gain a proton. And so your bottom number is actually going to go up by 1, but that gets balanced out by the fact that there's a negative 1 here for our beta particle. So once again, what number do I have here? I have 1. What number do I have over here? I have 2 plus a negative 1, or 2 plus a negative 1 is the same thing as a 1 that's there. So you're going to have a negative number on the bottom, and that is going to cause some mathematical problems if you're not careful. Let's check it out here. All the following atoms undergo beta decay. Well, every time we do beta, we do 4,2 helium. Oh, no, wait, that was alpha. We're not doing alpha now, we're doing beta. So remember that a beta particle is not the same thing as an alpha particle. A beta particle is 0, -1, and E. So I'm going to put down 0, -1, and E. That's there. Write that a little better. 0 and -1. And then I do the exact same thing I did with alpha. It's just that I'm doing it with a different particle. So if I've got 14 up top and I have 0, well, then that's pretty obvious. That's going to be 14 because my 0 and my 14 have to go together to make my 14 over here. So again, the numbers on the top have to be the same. 0 and then 14. That's there, like so. Now, this is a 6, and this is a -1. All right, now here it is. Here's your split. What number has to go here to go with a -1 to give you 6? Well, that number has to be 7, because if you add 7 and -1, -1 plus 7 gives you the 6. So the bottom number is actually going to go up in this case because you're essentially subtracting a negative. And if you remember from math, if you subtract a negative, it actually goes positive. So this 6 that's here loses a -1 and goes to a 7. Or, to put it a different way, remember that this is your split, and this is a 6, and this is a -1 and a 7. Everything over here has to be the same as everything over here. -1 and 7 is the same thing as the 6. All right, let's try another example. It says the following atoms all undergo beta decay. All right, so what was our beta particle? Our beta particle is 0, -1, and E, like so. So all I have to do is, oh, I'm sorry, I forgot here, number 4, I forgot to figure out what element this is. It's 14 and 7, but I forgot to figure out what element that is. Let's go back to this for just a second. What element is this going to be? Well, it's 14 up top and 7 down below. The only number that matters is the atomic number. So we check out our periodic table. There it is. It's nitrogen. My bad. Got all excited and forgot to finish that problem. All right. Back to number 5 here. So what happens? We undergo a beta decay. And what happens in a beta decay is we give off this 0 and -1 that's there. So I've got 234 up top, and I lost 0, so that means I still have 234. So that's easy. Now what about down below? Well, I started with 90, and I lost -1. So that means this number here has to be 91, because these two numbers here, that and that, those guys have to add up to be what that number is here. So 91 and the -1, so the 91 here and the -1 here go together to give me the 90 that's over there. So all I have to do now is make sure I don't forget to figure out what element that is. And I go back to the periodic table and I find element number 91. There he is. It's back to PA, protactinium, like so. So that is element P and A. That's there. One more. 137 and 55 with cesium, and again it's undergoing a beta decay. So what happens is I lose a 0, a -1, and an E. So I just have to make sure that that number up top is the same as these numbers here. So that's easy. That's still got to be 137 because that number there and that number there have to add up to be that number that's there. So 0 and 137 give me the 137. Easy breezy mac and cheesy. All right. So that's all that. Now what about the bottom numbers? I've got 55 and I've got -1. So what number has to go over here so that it goes with -1 to give me the 55? So that's got to be 56 because again, that number here and this number here, they have to add up to give me that number there. And 56 and -1 go together to give me the 55 that's there. So that is element number 56, and now I just have to check my periodic table to figure out what element number 56 is, and apparently it's barium, Ba. So that is Ba, like so. So that is beta decay. So, quick review. Alpha is a 4,2 helium. Beta is a 0, -1 E. Now you're going to love gamma because gamma is just the energy that comes off of there. It's no actual particle. And because it's just an energy, it's a 0 and a 0. So yes, it's just as easy as it sounds. If you start with 12,6 carbon and you give off gamma energy, you're going to end with 12,6 carbon because gamma is 0 and 0. It's just energy. There's no particles coming off of there. So consequently, if you're going to undergo gamma, what you need to know is that this is the symbol for gamma, or gamma is a 0, 0, and it's kind of a scripty looking V, kind of a U, kind of a squid looking thing there. So a gamma is 0, 0, gamma. So look, I'm not going to insult you with a whole lot of math here. If it's 240 and it's 0, it's 240. And then if it's 94 and it's 0 and then it's 94, it literally doesn't change. It's just the same thing. It's just energy that's coming off of here. So gamma is the easy one. So gamma is 0, 0, gamma, and this would be 60 and 27 and then CO that's there. So if we check back all the way up to here that's there, so this thing here, which about 15 minutes ago probably looked as foreign as like I was speaking Martian, now it makes a lot more sense. Alpha decay is 4,2 He. Beta decay is 0, 1 E, and gamma decay is 0, 0, gamma that's there. Those are the three things that you need to know. All right, handful more examples, and then you should be able to do this on your own, no problem. All right, each of the following isotopes undergoes an alpha decay. What is the daughter nucleus that results? Okay, so this is 214PO. Well, wait a minute, where's the number down here? You were so nice in the last ones. Why didn't you give us those numbers? Because it's really hard to type all those out, and you aren't necessarily going to see them that way. Plus, you can look it up yourself. All you got to do is find out what element PO is. So you go to the periodic table and you find element PO. There it is. It's element 84. So the number that's missing there is 84. No, I didn't give it to you, but I did kind of give it to you because I told you what PO was. And now what did I say? I said that each one of these undergoes an alpha decay. So if that's the case, then I'm going to lose 4,2 helium because that 4,2 helium is the alpha particle that's there. Okay, so then what is remaining? Well, 214, and I lost 4, so that's going to put me at 210. 210 that's there. And then I had 84, and I lost 2, so that's going to put me at 82. And now all I have to do is look up what element that is. And element 82 is the element lead, Pb. So this here is Pb. So lead 210 is the daughter nucleus that comes from an alpha decay from a polonium-214. What about this guy? Actinium-225. Well, let's see. Let's find actinium. Here he is. Actinium is number 89. So here we are. There's number 89. And it says it's going to undergo an alpha decay. So I'm going to lose 4-2 helium. Because every time it's alpha, it's always 4-2 helium. Always. So if I started with 225 and I lost 4, that's going to leave me with 221. And then if I started with 89 and I lost 2, then that's going to drop me down to 87. And if I'm at 87, then that would be the element francium, Fr. So that would be there, Fr. That would be your daughter nucleus that would come to this. What if you have some radioactive platinum here? So platinum 175, what goes on with him? Well, let's see. Let's find platinum. Here he is. And for some of you, this might be the longest process, is finding the element. Please be aware that they are alphabetically arranged here as well. You can always check down here if you don't know where they are in the periodic table or can't find them. So platinum is number 78. So the missing number down here is number 78, like so. And it says it's undergoing alpha decay, so that would be 4, 2, and helium, because it's always the same. 175 and 4 gets me 171, and then 78 and 2 gets me 76. So that radioactive platinum has turned into 76 osmium, OS. So that is OS. That is the daughter nucleus that results from an alpha decay of platinum 175. Each of these following isotopes undergoes a beta decay. What is the daughter nucleus that results? All right, so here we go. I've got lead 214. So I'm missing the number for lead. I just got to look it up. There's lead. Lead is number 82. So I'm going to have 82 that's down here. And this is now beta, so we're going to do the beta particle. So if you remember, a beta particle is 0, -1, and E. So that means up top, I've got 214 and 0, so I'm still at 214. But down below, I'm at 82, and then I'm at -1 and some other number. So that's got to be 83. So that the -1 and the 83 can go together, because those guys have to be together to make your 82 that's over there. So remember, everything on the left-hand side of the equation has to be the same as everything on the right-hand side of the equation so that it all balances out. So the 214 up top is the same as those two. The 82 that's down at the bottom is the same as those two put together. So what element is now element number 83? Bismuth, I believe it is. There he is. Yes, bismuth. It's number 83. Bismuth. All right. What if I have some radioactive potassium from your banana that's going to undergo a beta decay? What's going to happen here? All right, let's find out. Potassium is over here at number 19. So I'm going to come down here, and I'm going to say this is 19, and I'm going to undergo a beta decay. And every time I undergo a beta decay, it's 0, -1, and E, or sometimes we put it as the little beta symbol. Either one is fine. Don't care. What matters is the numbers. So I've got 42, and I've got 0. So that means up top here, my missing number is 42. Because again, these two numbers here have to add up to be that number over there. So the two connected on the right, 0 and 42, are the same as the top left, 42. What about the bottom left? I got 19. Then I've got -1, and what number has to go here? Well, that number has to be 20, because -1 and 20 have to go together to make the 19 that's over there. So what element has this turned into if I am now element number 20? I believe that's calcium is right next door. And it is. Calcium is number 20. That's there. So that is element calcium. So that is the daughter nuclei that shows up. What if I have some radioactive cesium that undergoes a beta decay? Got to know what number cesium is before I can start. There it is, number 55. So here's cesium at number 55, and it's going to undergo a beta decay at 0, -1 with an E. My top numbers have to be the same, so what number has to go over here? Well, that's obvious. That's 137, because 137 and 0 can go together to make my 137 that's over here. And then down below here, I've got 55 and -1. So 55 and -1 are going to go together to be 56. And the 55, -1, the -1 and the 56 go together to make the 55 that's over there. And so consequently, I look it up, and element 56 is barium. So that is Ba. That is there. 2 more to go, and they're the easy ones. So a gamma decay. A gamma is just energy, so we don't even need the bottom numbers here, because a gamma is 0, 0, and gamma. So we're going to end up with 137 in Ba. And then this guy down here is gamma, and that's 0, 0, like so, with gamma. And that's going to end up with 11 and B, that is there. So for each of these guys, gamma decay, it doesn't really change. It just ends up in a less energetic form over on the right-hand side. So consequently, what you've got here is you've got alpha, beta, and gamma decay. This guy here shows you each one of those. We've run through each of those particles. And again, just to summarize, alpha is that symbol, and it's a 4,2 helium. Beta is that symbol, and it's a 0, -1 E. And gamma is that symbol, and it's a 0, 0 gamma.